Thanks for waiting, people. Now we're gonna listen to Anthony in the next 20 minutes. He's working in our group, working with Richard Wood, and he's gonna talk about resumming Fermion loops for inflationary gravity.
So thank you to Boron and Roy for asking me to speak today, and thank you all for coming to hear it and bearing with us through the technical difficulties. So today I want to talk about a paper that I wrote with Professor Woodard over Christmas of this past year, titled Resumming Fermion Loops for Inflationary Gravity. Okay, I'll begin by just reminding everybody a couple of things about inflation and cosmology. Then I'll tell you what we actually investigated, talk a little bit about how to do it, and then tell you the results we found, what they mean, and inspiration for future work. Okay, so with the largest scales, the universe seems to be isotropic, homogeneous, and inhibits nearly zero spatial curvature. The geometry which tells you that is very close to that of flat space, except the spatial part is precluded here by this factor a squared of t. A of t is called the scale factor, and the reason for that is because it takes coordinate separations, scales them by a of t to convert them into physical distances. So for that reason, it gets the name the scale factor. While the scale factor isn't directly observable, there are two really important observable quantities which come from its derivatives. So that is the Hubble parameter, which is the logarithmic time derivative of the scale factor. That tells you about whether or not the universe is expanding, and the first slow roll parameter, epsilon of t, which tells you whether or not that expansion is accelerated or decelerated. That goes like minus h dot over h squared. Okay. When both the first and second time derivatives of the scale factor are positive, and that corresponds to having a positive Hubble parameter and the first slow roll parameter between 0 inclusive and 1, the universe is said to be undergoing something called inflation, a period of rapid accelerated expansion. And there's evidence to suggest that this is happening both now and at the earliest moments of cosmic history, during which time it gets the name primordial inflation. Okay, if we look back at those really early moments in cosmic history, we have an upper bound of the Hubble parameter being as high as 10 to the 14 GeV, and first slow roll parameter less than 3 parts in 1,000. This means that to an excellent approximation, we can take primordial inflation to be the geometry of de Sitter with a vanishing first slow roll parameter and an exponentially growing scale factor that goes like e to the ht. Okay? Doing any sort of calculations in this geometry, it becomes really easy if we switch over to open conformal coordinates, where we redefine the co-moving time t according to this, and have our conformal time eta run from minus infinity to 0. The reason that makes life so easy is because then the metric just becomes a squared times the flat space metric. So it becomes easy to work with. Okay? One of the things that happens during inflation is that there's something called inflationary particle production, where lots of massless scalars and gravitons are produced and ripped out of the vacuum. So for example, the occupation number of a massless scalar goes like this. It grows exponentially like a squared. The reason that this happens is twofold. One is that neither of these guys are conformally invariant, and that's the piece which allows the occupation number to grow exponentially like a. The other key piece is that they're massless, so for long wavelengths, that is the part that allows them to be ripped out of the vacuum and propagate forever so that we might be able to see them now without violating the energy time uncertainty principle. Okay? Speaking of gravitons, I want to tell you about how we define the graviton field in this geometry. So the way we do that is by subtracting off the background from our conformally rescaled metric. So that's defined here as g mu nu of x goes to a squared g tilde mu nu of x, which includes both of our background and our graviton field h mu nu. And our loop counting parameter, kappa squared, goes like 16 pi g, and every time we get a loop, we get one. Okay, with that out of the way, I can tell you about what we actually found. So we're interested in investigating the gravitational response to fermions. The way we do this is by taking quantum corrections to the linearized effective field equations. Okay, that is given by equation 8 here. Looks a little bit different than how we're used to seeing the Einstein field equations. So I just want to take a minute to talk about that notation. So the first piece here, this 4-index operator L is what's known as the Lichnerowitz operator. Its whole purpose is to act on the graviton field H mu nu to produce the variation in the Einstein-Hilbert action with respect to the graviton field to linearized order. So since it's the variation of the gravitational action with respect to the graviton field, the way to look at this is that it contains all of the same information as the typical left-hand side of the Einstein field equations. So for all practical purposes, is to think of this guy as the Einstein tensor g mu nu plus lambda little g mu nu. Okay. The right-hand side is the usual expression of our of our stress energy in the problem, and the quantum corrections come in through this guy. So this 4-index object here, mu nu sigma rho sigma of x and x prime, is the one-particle irreducible graviton 2-point function, and that gets the name graviton self-energy. So taking the graviton field, integrating it up against its 1pi 2-point function, and adding it as a source term is what puts the quantum corrected in quantum corrected linearized field equations. Okay? I do want to point out that this is a very generic technique for quantum correcting equations. If you were to do this for a scalar field, you would integrate the scalar field up against its 1pi 2-point function, the self-mass, add it as a source term. Do the same thing for vector fields with its vacuum polarization, and this is how you quantum correct classical field equations. So we're going to do that. We're going to do it for two key sources. One, where the stress energy is identically zero, corresponding to gravitational radiation, and one, the second, we're going to investigate when T mu nu is that of a point mass, and look at corrections to the Newtonian potential. Okay. So we need to get the self-energy, but before we actually go ahead and calculate that, I'll tell you a little bit about the Lagrangian of the setup, mainly how it differs from its flat space counterpart. So we're going to be talking about the Dirac-Lagrangian. In flat space, we know that just goes as psi bar I d slash psi. So we need to do that in curved space. And the way we take this Lagrangian from flat space to curved space is how we do it for all Lagrangians, is that we need to make it preserve general coordinate invariance. The way we do that is by tacking on a factor of the square root of minus g as usual. And the problem here is that this derivative will no longer be covariant. So we have to essentially define a covariant derivative that is both spin and metric compatible. Doing that requires the use of three things. One is the Vierbein field, which based on this definition here, takes two of them plus the Minkowski metric to get you back to the full metric. So you can think of it as a metric square root. We need the spin connection in order to make that derivative, both spin and metric compatible. And the spin generators here are just commutators of gamma matrices. Okay, so those three guys combine in exactly this way to give us the covariant derivative that we need. Okay, one comment I want to make is that this Lagrangian here for massless fermions is conformally invariant in any dimension. So what I mean by that is that when you rescale your fields appropriately, so g gets sent to a squared g, and psi gets sent to a to the d minus 1 over 2 psi tilde, when you substitute all of that into your Lagrangian, you can see that you could express all of the fields in the tilde. So mainly we have no d-dependent factors of a hanging out front. So it looks the same in the tilde fields as it does in the regular fields. Since there's no factors of a, we say it's conformally invariant for any dimension. Okay? That is an important piece. So since the Lagrangian no longer depends on A, we're going to see that when we calculate the self-energy, no factors of A can enter the calculation except through renormalization counterterms. Okay? And one other piece of information we'll need is the Fermion propagator, which we get in the usual way by taking the vacuum expectation value of the time-ordered product of two Fermion fields, one at x and one at x prime, and it looks as such. Okay, so from that Lagrangian, we'll read off three diagrams that are going to, in principle, contribute to the graviton self-energy. The two diagrams on the left make up the primitive contribution, and this diagram on the right is for renormalization counterterms. The one on the left, made up of two vertices, one at x and x prime, is known as the 3-point diagram, and the one in the middle, made up of the one vertex there, is known as the 4-point diagram. As it turns out, when you calculate these guys in dimensional regularization, the middle one is going to vanish. Okay, so that just leaves us needing to get the 3-point diagram to figure out the primitive contribution. Okay, so how does that diagram actually contribute to the self-energy? Well, we need to take into account the two vertices, one at x and one at x prime. And the way we do that is by functionally differentiating that Dirac action with respect to the graviton field. So we take its product, evaluate it when the graviton field is 0, and take its vacuum expectation value. One of these guys is going to look like this, involving the derivatives of psi and psi bar. And when all is said and done, you plug it in, calculate it. After lots of computations, it's going to look something like this. So I want to highlight this main result and talk about a couple of important features that it has. One is that since it's written in terms of these projection operators here, it's manifestly transverse and traceless. Another thing I want to highlight is that it also happens to be conserved, which is good. One issue with it that we can see immediately is to be able to do any sort of calculations in effective field theory in 4 dimensions. It goes like 1 over d minus 4, so we have some bad divergences in the theory. But that's okay, because as it turns out, we can use this counter-term Lagrangian, and we showed long ago that this can renormalize any matter loop contribution. Okay? So the first term here is an r² counter-term. What that guy does is that if your self-energy were not already transverse and traceless, you could adjust C1 to make it so. Ours already happens to be, so we don't need to worry about that. The purpose of the Weyl squared counterterm, which gets that name because it's 2 Weyl tensors contracted into one another, will help us remove those 1 over d minus 4 divergences. So the way we figure out how to adjust those coefficients, C1 and C2, is to compute the contribution to the graviton self-energy for this counterterm Lagrangian, and then choose them to cancel the divergences. As it turns out, if you choose C2 to go like this, with renormalization to scale mu, you'll cancel the divergences, and then you add that contribution to the primitive contribution. So the final in-out graviton self-energy goes like this. Okay, a lot of work to get there, but we got it, and it seems like, naively, that we can start doing effective field theory with it. But you may notice 2 things, 2 problems with this, is that this renormalized self-energy is not real and it's not causal. Since we're doing effective field theory, we want to be able to do causal and real-valued physics on real-valued spacetime. But there's a really neat way to fix this is by converting from the in-out formalism to the in-in formalism, which is also called the Schwinger-Keldysh formalism. Doing that gets rid of these pesky factors of I, and it also enforces causality through this theta function here. So this is the appropriate way to include the self-energy in your quantum-corrected effective field equations. Okay? Now that we have it, I could actually talk about solving it and giving you some results. So the effective field equations for 0 source term corresponding to radiation goes like this. It's the same equation before, just with T mu nu equals 0. We're going to be investigating it for plane wave gravitons, which go like this. So kappa h mu nu, the graviton field goes like a polarization, the same one that it is in flat space, meaning that it's transverse, traceless, and purely spatial. Our plane wave part, and a graviton mode function, which depends on the conformal time and the magnitude of the wave vector. But since we only know our graviton self-energy to 1 loop order, that means that we need to solve this perturbatively. So we expand the mode function in powers of the loop counting parameter. The tree order result is purely classical, so not worried about any quantum corrections, just simply taking the left-hand side of the field equations and setting it equal to 0, and we get a solution that looks like this. First order is where the quantum corrections come in, and the way you do that is by taking our tree order result, putting it into the integral to integrate it up against the graviton self-energy, and acting the Lipnerowitz operator on the first order correction to set up a differential equation for U1 and solve for it. Okay, so that permits a solution at late times. And the way that solution goes is like this. And the first thing, the most striking feature about it is that it grows like the logarithm of A. So it has some secular growth to it. The way we repackage this is, so in order to demonstrate this growth of the correction, we repackage it into the electric part of the Weyl tensor, C0I0J of X, which goes like the tree order result, plus a correction that goes like GH squared times the logarithm of A. So we get secular growth in the 1 loop correction. Without going into as much details, I'll tell you what happens to the Newtonian potential with the stress energy of a point mass, is that we get a 1 over r squared correction. That's nothing too surprising. It's just the de Sitter analog of something you would see in flat space. But we also get a secular growth part here that again goes like the logarithm of a. Okay, so that's what we found to one loop order for these massive fermion contributions to gravity. Okay, there are two issues though, is that during a prolonged period of de Sitter inflation, even though this guy goes like the loop counting parameter, which involves gh squared, which can be very small, no matter how small gh squared is, if you wait long enough, these first order corrections are going to grow secularly and completely overwhelm the tree order results. At that point, the first order corrections are no longer perturbatively small, which means that perturbation theory breaks down and it fails you. So in order to be able to get around this, we need some sort of non-perturbative resummation scheme, and hopefully to be able to do this to all orders. And as it turns out, we can do that using the renormalization group, or a variant of the renormalization group. Okay? The way to do that is to regard both the Weyl tensor and the Newtonian potential as being two-point Green's functions, and to invoke the Callan-Zemantic equation for that two-point Green's function. So that involves derivatives of, with respect to the logarithm of the renormalization scale, the beta function, which happens to be 0 to the order we're working in, and the gamma function. So a comment on derivatives with respect to the log of the renormalization scale. We saw from our self-energy before that after we're done removing the divergences, we express it in the Schwinger-Keldysh formalism. Every time we get a logarithm of a, we get a logarithm of mu. So we can go ahead and just swap out that log of mu with log in a and differentiate with respect to that. Gamma comes from a field strength renormalization. It's explicitly given by kappa squared h squared over 160 pi squared. The field strength renormalization is here. That guy is completely determined by the coefficients of your renormalization counterterms. And when all is said and done, and you go ahead and solve this equation for the Weyl tensor and the Newtonian potential, you get that. Okay, I'm basically at the end. And when you go ahead and solve that for both the Weyl tensor and the Newtonian potential, they grow like this: the tree order result times the scale factor, which goes like gh squared in the exponent. So what we've done is, if you know the coefficients of your renormalization counterterms, that completely determines the resummation scheme using the renormalization group analysis. So it took a lot of work, doing a lot of pesky calculations to even just be able to get our one loop corrections before. And this provides a quick and elegant way to resum the results to all orders, and not having to sit there calculating 2-loop results, 3-loop results, and so on and so forth, and that they combine like this. Okay? So we felt that was an important result, and it actually gave us a couple of spin-offs for future work that I'll briefly tell you about. One key thing is that we actually did not have to make any assumptions about what the scale factor was in doing these calculations until we plugged them into the field equations. Remember before I told you that because these massless fermions are conformally invariant in any dimension, that the self-energy did only dependent on A through renormalization counterterms. That means we can go ahead and solve this for any cosmology. We don't actually have to specialize to de Sitter. All we need to do is work out what the Wittenberg operator is for that cosmology. And also the current work is to try to extend this analysis to massive fields, which are a lot more difficult to do this for, but I could talk about that another time. Okay, well, that's all I have. Thank you, everybody.